Okay, first of all, schedule for this week, for this class, next class. So today we're gonna finish chapter 2, which is the longest chapter and obviously the most difficult chapter for this class. Okay, so we're gonna finish chapter 2 today, and then we're gonna start doing some practice questions together. Okay, today and also Tuesday next week. Okay. All right. So last time we stopped here. All right. So asked us to calculate the covariance. Okay. Covariance, and which is mu xy minus mu x times mu y here. Okay. And last time we calculated mu x times y, which is the mean value of x times y, which is equal to 4/9. Okay, 4/9. And then let's get the mu x and then the mu y. Okay. One more thing I will say is chapter 2, especially the later section of chapter 2, such as this, jointly distributed random variables are very, very complicated. Okay, so do not get frustrated if you cannot fully follow it. Okay. Okay, mu x, the mean value of x. So we do the integration of x, x. This is the marginal, okay, the marginal function of x times dx, okay, and we need to get the marginal function f(x)(x), okay, and the marginal function is equal to fxy, which is 8xy. Okay, so dy, okay, and for the range of dy we need to fix the x. Okay, what does that mean? So fix x for a certain value of x. Okay, the value for y is between 0 and x. Okay, so that's why we have integration between 0 and x. Okay, so that will become 8x to y squared from 0 to x. So f(x)(x), the marginal function, will be equal to 4x to the power of 3. Okay. All right. And then we can plug this marginal function into mu x. Okay. So for mu x here, the range for dx for x is between 0 to 1. Okay, so the range is from 0 to 1. X, marginal function f(x) is 4x to the power of 3. Right here. Okay, dx. All right. Okay. So mu x will be 4/5. Okay, so we get mu xy and then we get mu x. Okay, the next one gonna be the mu y, the mean value for y. Okay, so third step we get mu y, so very similar to mu x. So mu y is do the integration for y f y y d y. Okay, and we need to find out f y y, which is the marginal function for y. Okay, so let's figure out f y y first. So that will be integration for fxy, which is 8xy dx. Okay. And the range is between y to 1, which is when we fix y, when we fix certain y value. Okay, so the range will be this point, which is x equal to y, because this is the line of y equal to x. So this is y to 1 here. Okay, so that's why the range is between y to 1. Okay, so 8xy is fxy, right? 8y to x squared, so between y to 1, so that is okay. Right, so that is marginal function fyy. Then plug that number here. The range for y is between 0 and x. Again, the range for y, okay. Oh, sorry, 0 to 1. From 0 to 1, it's mu y. Y times fyy marginal function dy. Okay, so y the range is 0 to 1. Okay, so when we fix x, that value is between 0 and 1. So mu y will become 4y squared minus 4y to the power of 4 from 0 to 1. And then this is mu y. Okay, so finally we get mu xy, which is 4/9 here, minus mu x times mu y. So mu x is here, 4/5 times mu y is here, 8/15. So 0.01778. Okay. As you can see, the procedure is very very complicated. You should be able to follow the steps I read here and know why we should take the range of, for example, 0 to x, 0 to 1, or to y to 1. Okay, but I do not expect we see similar kind of problems in your quiz or exams. Okay. Correlation.
Wait,
Yes.
I have a question.
Could you
just mentioned
scroll back up, please?
You just mentioned like quizzes and stuff. Do you know when those will be?
Yeah, I will see. This we are at end of chapter 2, right? And the chapter 3 is kind of short chapter, which take about 1 week. And chapter 4 take about 3 weeks, I will say, at least. Okay. And then we're gonna do some practice sessions. So the first quiz will be at least 4 weeks from now. Okay. And
Oh, really? Okay.
yeah. So yeah, I will let you know well beforehand. Okay. And
And we'll have one homework assignment after chapter 2, right?
yeah, gonna be today after the class. I will assign the first homework. Okay. And also today and next week we're gonna do the practice section. You know, we do all the some questions from chapter 1, chapter 2 together. Okay. So we can prepare you for the first homework. Okay.
Okay. Thank you.
Professor,
Yes.
I know you said that these type of problems aren't going to be included in our exams or in our quizzes, but could you just discuss how this fractions turn into a decimal approximation? And if we were going to do this, would we want to leave it in exact form or have it in a decimal approximation to 3 significant figures, or just leave it the way that it is right now?
Three or four, maybe better for significant figures will be good. Okay, yeah, yeah, but you know, don't worry too much. I will give up, you know, percentage of error. So that part is okay. So don't worry about that.
Okay.
Okay, okay. Other questions before we continue? All right, correlation. So correlation, seen from this equation, correlation is rho, because rho xy is a function of covariance COV xy, as we just discussed in the previous slides. Okay. So correlation between xy is given by this equation. Okay, and if the question is asking the correlation for x and y, we can just using what we found it from the previous example. So covariance here is 0.01778. Okay. 0.01778. Okay, hold on. And then we're gonna find out sigma x and sigma y. Okay. Okay. So sigma x and sigma y. So sigma x is the variance of x. So based on the previous equation, which is the equation you can find from slides 108. Okay, slides. So that's the equation for sigma square variance. So this is f(x) marginal function dx minus mu x square. Okay, and the range is between 0 and 1. So x squared and f xx, the marginal function we just found out 5 minutes ago. This, okay, dx minus mu x. Okay, mu x we just found out is 4 over 5 squared. Okay, it's here. Mu x and mu y, 4 over 5. Okay.
Professor, is that a density notation?
Yeah, we call that rho correlation. Rho doesn't
Yeah.
only mean density, but yeah, could be rho. You know, in physics, yeah, it means density, but here it means correlation.
Okay, correlation.
Yeah, correlation.
Thank you.
Yeah. Okay, so this is 0.02667. Okay. And similarly for y, so y square marginal function fy y dy minus mu y square. Okay, so the range is still 0 to 1. Okay, so fyy also we just found out in the last slide is this. Okay, y square okay dy okay, and mu y is also we found out here 8 over 15. Okay, so just see what sometime we do the integration 0.04889. Okay, so we can plot sigma x and sigma y, that is the square root of that, okay, into sigma x, and the square root of sigma y square is sigma y. Okay. All right. And the next slide tells us about the correlation, covariance, and independence. Okay, so let's just read it together. If the covariance and correlation both equal to 0, okay, and then we call x and y are uncorrelated. Okay, if x and y are independent to each other, then they are also uncorrelated. So if independent we can conclude they are also uncorrelated. Okay. However, if it's uncorrelated, we cannot 100% sure it is independent. Okay, but in practice, that rarely occurs. But still, when it is uncorrelated, does not guarantee they are independent. So doesn't mean 100% they are independent. Okay. All right. Okay. So if things is still not complicated enough, here is the more than 2 random variables. So if we have n random variables, x1, x2, and xn, and the c1, c2, cn are constant. Okay, and then the mean value. So this is the mean value of c1, x1 plus, again, this is not L, this is dot dot dot, plus cn xn is equal to c1 times mu x1 plus dot 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 plus cn mu xn. Okay, and the variance of c1 x1 plus dot 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 plus cn xn is equal to this equation. This is c1 square variance of x1 plus dot 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 plus cn square sigma xn square. Okay, and this is the sum of, this is the covariance. Okay, so if x1, x2, xn are independent to each other, and this part will become 0. Okay, so otherwise we use this. Okay, as I said here. So if x1, xn are independent of each other, the previous two equations will simplify as this. Okay, because the covariance is equal to 0 now, if they are independent. Okay, still the previous example, the mobile computer moves from a random position, okay, x, y, vertically to the point of x0. So that's drawn here. So from a point, let's see, this is xy. Okay, so vertically to the point of x0. So this is this part. This point, this is x0. Okay, and then along the xl to the origin. Okay, so this is from this point here, and then go back to 0, 0, to 0, 0, origin. All right. So the distance is traveled is this part. So this part is y, right? This distance is y, and then plus this distance, so that is x. Okay. So the distance is traveled is x plus y. Okay. So find the mean value and the variance of the distance traveled. Okay. So the mean value of x plus y. Okay. So based on the previous equation, the mean value is c1 mu x1 plus c2 mu x2, blah blah. Okay, so that's the mean value of x plus the mean value of y. Okay, so both of these two values is done. We just calculate them. Okay. Right. And for the variance of x plus y, okay, that is equal to variance of x plus variance of y plus 2 covariance xy. Okay, so this is because based on this equation. Okay, and luckily we get sigma x sigma y 0.04, and also the covariance all resolved. Okay, 0.01778. Okay, all right. Yes.
So the first two numbers in the solution are squared,
Yeah.
and then the last is just a multiplication. Okay. So
Yeah, it's here. It's the based on this equation. The variance C1 is constant. In our case, the C1 is 1. Okay. Right? And the C2 is also 1. Okay. 2 constant 1 1 covariance. Okay.
Could you just leave it here for just a little bit? I
Yes.
want to finish.
Yes. Yeah, this will be our last
0.
slides, basically, for chapter 2. All right.
So the last number in there, that's 2 times 0.01778.
Yeah, that's the covariance. 0.0177.
Okay.
Yeah. Yeah. Oh, by the way, I put a hard copy of the textbook in my mailbox. If you need it, you can get it now.
Thank you.
Yeah. So basically, all of these problems is also discussed in the textbook. Okay.
Thank you.
Okay. All right. Summary. Chapter 2. So what we did for chapter 2? We discussed probability and the rules, the counting method, which is very, very important. And I want everybody to know how to do the counting method, when to use combination and when to use permutation, if you still remember, and what is conditional probability, and what is independence. Okay. For random variables, we know we have discrete random variables, and we have probability mass function for discrete variables, and then we have continuous variables, and we have probability density function for continuous variables. Okay, so this is mass function for discrete and density function for continuous variables. Okay, and also we know what is cumulative distribution function. Okay, so we just do the sum or do the integration from the negative infinity to the number we are interested in. Okay, and then the mean value and variance for the variables. Linear function is okay. Mean and variance of sample mean. The last part is very complicated. When we have more than more than one random variables, we call that jointly distributed random variables. Then we will have a marginal function and a conditional function. Things will get very complicated as you see this week. Okay, but again, don't worry. Focus on the early part of this chapter. Okay, so this, okay, and also this. All right, so that's the end for chapter 2. Then we're gonna do some practice problem together. Okay. So let me do. Sorry. All right, good.
Are all these practice problems that we're going to do in the book also?
Yes, the practice questions also coming from the book. Yeah, okay. So this is the questions we're gonna discuss today and next week. Okay, all these questions coming from chapter 1 and 2. First question is on page 12, question number 2. Here, this is a basic concept. Okay. So if we want to estimate the mean height of all the students at a university, so which one of the following sampling strategies would be the best? Okay. Why? Okay. Know that none of these methods are true simple random samples. Okay, so let's look at all this method. First one, measure the height of the 50 students found in the gym during basketball interment. Okay, of course, that will overestimate the average height, right? So a basketball player will be taller, much taller than average students. Okay, and the second one, measure the height of all engineering majors. Okay, I cannot say exactly why, but from engineering majors, then it is still more likely that will be somehow different from the whole university on average. Although the difference will not be as big as the basketball instrument, okay, basketball team. Okay, so the second approach is better than the first, but let's look at the third one. The third one will be better. So measure the height of the students selected by choosing the first name on each page of campus phone book. Okay, so think about this process. This is very unlikely that the students whose name happen to fall at the top of page in the phone book will differ systematically in the height from the population as a whole. Okay, so I will say the third one will be the best. Okay, it's close to a simple random sample. The second is from engineering major is better than the third one from the basketball intramural. Okay. Right. So when it is possible, always choose a simple random sample. All right. So that's the first question. So let me know if you have any comments or question. Number 4.
I'm sorry, just to clarify, Professor, the last solution, even though it wasn't described at it as an option, that's a simple random variable, the third option.
That's not a truly simple random variables, but it's still close to much better than the other two options. Yeah.
Okay.
Yeah. Okay. So question number 4. Sample of 100 college students selected from all students registered at certain college, and turned out 38 of them participated in intramural sports. So true or false? The proportion of students at this college who participated in intramural sport is 0.38, which is 38 divided by 100. Okay, so this is not true. Okay, so we take 100 students, that's a sample, and the sample proportion is 0.38. So it doesn't necessarily mean the whole population is also 0.38. So A is not true. B is true. So B says the proportion of students at this college who participate in intramural sport is likely to be close to 0.38, but not equal to 0.38. Okay, right. So this is correct statement.
Is that a description of a certain classification of statistics?
Yeah, in statistics, basically you try to get the parameter, or in this case, the proportion participating in intramural sport of the whole college or the whole population from a sample, from these 100 students. Okay, so from this sample, 100 students, you found out the proportion is 38%. And you want to get the idea, how about the proportion for the whole college? Okay, so that's close to 38%, but not exactly 2. We're gonna answer questions related to this in future chapters, like chapter 4, 5, and 6. Okay, such as confidence interval and hypothesis test. Okay, so yeah. Next question. 5. A certain process of manufacturing integrated circuits has been used for a period of time, and it's known that 12% of the circuits is produced are defective. Okay. a new process supposed to reduce the proportion of defective is being tested and get a simple random sample of 100. Find again 12 are defective. Okay, so look at question number 1. So one of the engineers suggests that the test proved that the new process is no better than the old process because still get 12 over 100. Okay, so is this conclusion justified? Explain. Okay, so we want to know what is the percentage of the whole population is defective. Okay, and as we just discussed, the sample proportion, which is 12 over 100, is only estimation. Okay, it's not the same as the population proportion. Okay, so the population proportion of the new process may actually be higher than 12% or lower than 12%. So based on this information, we cannot just give a conclusion. The new process is better or not. Okay. B. Assume that there has been only 11 defective circuits in a sample of 100. So 11 over 100 says 11%. So that is actually lower than the old process, which is 12%. So would this help prove that the new process is better? Okay. Still, the answer is no. Okay. The population proportion for the new process may be 11%, maybe 10%, maybe 12%. Okay. So based on this limited information, we cannot conclude the new process is better. Okay, so again, we're gonna learn this, how to answer this type of question from chapter 5, which is confidence interval. Okay, so for example, we are 95% confidence or 90% confidence that the new proportion will be somewhere between a certain range. Okay, but for now, with this information, we cannot draw that conclusion. The new process is better or not. C. Which outcome represents stronger evidence that the new process is better? Okay, so finding 11 defective circuits in the sample, or finding 2 defective circuits in the sample. Okay, so everybody knows, of course, 2 defective circuits in the sample, that's only 2%. So the sample for the new process shows only 2%. And then the chance, the defective proportion in the new process is still 12% is very, very low. Okay, so that's very, very high chance the new process will have lower defective percentage than 12%. Okay. However, finding 11 defective circuits in the sample, we cannot really draw a meaningful conclusion. The new process is better or not. So, finding 2 defective circuits in the sample will have much stronger evidence that the new process is better. Okay. And later on, we will learn how to quantify our confidence level based on the sample information. Okay, that's question number 5. Then page 23. So page 23, question number 2. All right. So this is also about the basic idea. Is the sample mean always the most frequently occurring value? Okay. By the way, the most frequently occurring value is not the sample mean; it's called mode. Right. MODE. Okay. If so, explains why. If not, give a example. Okay. So answer is no, of course. Give an example. So let's see. Easy. We have a sample. Let's see, 1, 2, and 4. Okay. The mean value is 1 plus 2 plus 4 divided by 3, right? So the mean value is 7 over 3. Okay. So that's not, 7 over 3 is not occurred at all. Okay. So again, the most frequently occurring value is called mode. Okay. For example, if we have 1, 2, 2, 4, and then the mode will be 2, which is most frequently occurring value. Next question, number 4. Is the sample median always equal to one of the value in the sample? If so, explain why. If not, give an example. This is also not true. The median is, remember, is n plus 1 divided by 2. Okay, and depending on it is integer or not. Right? So if integer, that will be that number of sample, that's the median. If not, we take the value on the right and the left. Take the average of value on the right and left. So for example, so we have 1, 2, 4, and 5. Okay, the median will be, we calculate 2 n plus 1 divided by 2. Okay. So n plus 1 divided by 2. So n is the sample item. So sample item is 4. 4 plus 1 divided by 2. That is 2.5. Okay. So 2.5 means the median will be the average of the second item plus the third item divided by 2. Right? The second item is 2. The third item is 4. Okay. So the median will be 3. Okay. So 3 is none of these sample items. Okay. So that's question number 4. Question number 6. For a list of positive numbers, is it possible for the standard deviation to be greater than the mean? Okay. If so, give an example. If not, explains why not. Okay. So what is standard deviation? We know the equation for standard deviation, but what does standard deviation tells us? Okay. So standard deviation, we call that sigma. So sigma tells us about the spread, or we call that the range of the value. Okay. So if the sample item are very close to each other, then the sigma or the standard deviation will be small. If the value has a very big range, then sigma will be larger. Okay. So let's give an example. We have a sample item of 1. Questions? Okay. Yes.
Is you're saying that sigma equals spread divided by range?
No, sigma tells about the spread, or the difference between the sample items, and we have the equation to calculate the sigma, which is a function of mean value.
Okay.
Yeah.
That's what it.
Yeah. Okay. So for example, for these 3 sample items, we have 1, 2, and 12. 12 is much larger than 1, 2. So the mean value will be, 1 plus 2 plus 12 divided by 3 is 5. Okay, and if we calculate the standard deviation, okay, skip that, you can calculate based on equation, is 6. Okay, so the sigma is, in this case, is larger than the mean value. All right. Okay, so that's question number 6. So sigma tells us about the spread of the value. Question number 8.
And so the answer is yes.
Yeah, it is possible for standard deviation larger than mean. Yeah. Then question number 8 here. 8 is here. In a certain company, every worker receive a $50 per week raise. Okay. How does this affect the mean salary? Okay. How about the standard deviation of salary? All right. So without knowing the individual income before the raise, okay. So just think about what the mean value is. Okay. So if everybody gets $50 increase, then the mean value of the new salary will be $50 more, right? Because everybody get increase of equal value, $50. So the new mean will be the old mean plus 50. Okay, so the mean value will increase by $50. How about the standard deviation? Anybody want to have a guess without calculation?
Stays the same.
Correct. Why?
Because you're just moving the mean, and like the data is basically the same thing in terms of like how it's spread. You're just changing like its
Exactly.
value, but the
Great.
spread is the same.
Yes, great answer. No, I just talked, sigma standard deviation tells about the spread or the range of the value. Okay, so think about these data points. When every data point increase by the same value, $50, then just move to the right altogether. So the spread does not change at all. So the sigma does not change at all. So standard deviation remain unchanged. Okay, so very good answer. That is question number 8. Okay. And then question number 10. So here we do some calculation altogether. Okay, very easy. A sample of 100 cars driving on freeway during a morning commute. Number of occupants in each car was recorded, and here as the result. Okay, for example, 70 cars has only 1 occupant, and 15 cars has 2 occupants, and so on. Question number 8. Find the sample mean of the occupants. Okay, the sample mean, we just add all the sample value together, right? So from 1 to 100, and divided by n, divided by 100. Okay, so because we have 70 cars has 1 occupants, so 70 times 1 plus 15 times 2, 15 cars has 2 occupants, plus 10 times 3 plus 3 times 4 plus 2 times 5, right? And then divided by 100. Okay, so that's sample mean. Sample mean is 1.52. So it tells us on average for each car we have 1.52 occupants. All right.
I'm sorry. Could you explain
Oh,
the summation
oh,
notation? So there's 100 over the summation. And there's x1. And then does that n2 equals 1 underneath the sum? The sum.
underneath, yeah, this is divided by n, which is 100 in our case. Okay, the sample mean. Sample mean is just we add all the value together and divided by the number of value. That's sample mean. So all the value added together is this. So we have 70 cars has 1. Okay, the 70 times 1. We have 15 cars has 2 present. 10 cars has 3. 3 cars has 4. 2 cars has 5 occupants. So that's total number of occupants in these 100 cars. Okay, and divided by the number of cars, which is 100, so that's 1.52.
Okay.
Okay. Let's continue. B, find the sample standard deviation. Okay, the sample standard deviation equation is here. Good. Okay, so the sample standard deviation, we call that S. Okay, and we have population standard deviation. Okay, the equation will be similar, but that's no minus 1 here. Okay, n is the sample size, and this is the sample mean. Okay, so the sample variance is asking for the sample standard deviation. Okay, so that is square root. Okay, so n minus 1 is 100 minus 1. All right, still we do the sum. So that is also equal to we should use another equation, which is okay, we can use this. Sorry. So we have 70 cars has 1 occupants, so that's minus the mean value 1.52 square, and we have 15 cars has 2 minus 1.52 square, and so on. 3 cars. Okay. So after calculation is 2.9372. Okay. So in the exams, you do not need to do this manually. Okay. You can use function for standard deviation. Okay. I don't really care. You know, as long as you know which equation to use, the calculation, how you do that is okay. I don't really mind. Okay. Let's continue. The find the sample median number. Okay. Sample median is the 50th percentile. Okay. Because when we do the median, we need to calculate n plus 1 divided by 2, and depending on it is integer or not, it is not integer, it's 50.5. So which means we should take the average of the 50th and the 50th and 51st value. So average of 50th and 51st value. Right. So which one is the 50th? The 50th, first we arrange the number of occupants from small to large. So the 50th will be what? What is 50th value?
1.
1, right? Because we have 70 cars has only one occupant. So the 50th will be 1. Okay? And also the 51st is also 1. Right? 51st is also 1 plus 1 divided by 2. So that's 1. So the median is 1. Median is 1. Okay. So these questions, we review the basic concepts and how to calculate them. Okay. D. What is first and third quartile? So the first quartile is 25th percentage, and the third quartile is the 75th percentage. Okay. So the first quartile is we do this 0.25 n plus 1. Okay, and then n is 100. All right, so that is somewhere between 25 and 26. So we should take the average of 25th plus and the 26th value. Okay. All right. And again, the 25th value will be 1, and so does the 26th value. So that is 1. Right. And for the third quartile is 75%, 0.75 times n plus 1. Okay. So that is somewhere between 75 and 76. So 75 point something. Okay. So the average of 75th and 76th. All right. So what is 75th? Okay. What is 75th value?
2.
2. Okay. So we have 70 has 1 occupant. We have 15 has 2 occupants. Okay. So 70 plus 15 is 85. Okay. So the 75 will be have two occupants. Okay. For 76, it also has 2. Is here one of these 15 cars has 2 occupants. Okay. So 2 plus 2 divided by 2 is 2. Okay. So as long as you understand what the question is asking, you can use corresponding equation to figure out the number. Okay. What proportion of cars has more than the mean number of occupants? Okay. So first of all, the mean value we just calculate. The mean is 1.52. 1.52. So how many cars has more than 1.52 occupants? Okay. So 2 cars. For 2 cars, we have 15 of them. And 3 cars, 10. 4, we have 3. 5, we have 2. Okay, based on the table. So that is equal to 30 total. So we have 30 cars more than the mean value, which is more 1.52. So the proportion will be 30 over the total number 100, 0.3. Okay, so very easy. F, what proportion of cars was the number of occupants more than one standard deviation greater than the mean. Okay, so more than one standard deviation greater than the mean. So this is the mean. One standard deviation, 0.9372. So that's the sigma, the standard deviation. That's the mean. Okay, so that is 2.54. Okay. Okay, so how many of them has more than 2.5? Okay, so 3 does count. So we have 10 cars has 3 occupants. For 3 cars has 4 occupants and 2 cars has 5 occupants. Okay, so that is 15. Okay, so the proportion is 15 over 100, 0.15. Okay, very straightforward. Last question for this, last part of the question for this question. Number 10, G. For what proportion of cars with the number of occupants within one standard deviation of the mean? Okay, so within one standard deviation of the mean. So that is the mean 1.52 plus minus standard deviation 0.9372. Okay, so within that range, okay, between 0.58 to 2.45. Okay, so yeah, of these 100 cars, we have 70 has 1 occupants, and we have 15 has 2 occupants. So 1 and 2 is within this range, right? So that's 70 plus 15, that's 85 cars, right? So divided by 100, proportion is 0.85.
I'm sorry, could you explain why we're doing the plus or minus in that equation?
Is that question is asking for what proportion of the cars was the number of occupants within one standard deviation of the mean. So within could be larger,
Oh,
standard
okay.
deviation larger, or one
I get
standard deviation smaller. Yeah. Okay, good question. All right.
And that's the second figure is 2.4572.
Yeah. That's 2.4572. Sorry. It is plus the standard deviation. Okay. Yeah, sorry, for my handwriting is already very bad, but when I write it with my Apple Pencil on the iPad, it's become even worse. Sorry. All right, here's question number 10. It's here. Okay, I think let's stop here. This is the practice question for chapter 1, and then we have these questions for chapter 2, which will continue Tuesday next week. Okay, so let's stop here and have a rest.